Before we start, make sure you like this video, subscribe to the channel, and turn on the notification bell so you never miss a new upload. And if you have ideas for future videos, drop them in the comments below. Also, watch until the end, because what happens to time inside a black hole becomes more mind-bending the deeper we go. Imagine watching the entire future of the universe unfold in front of your eyes. Galaxies forming, stars being born and dying, civilizations rising and disappearing, all happening faster and faster like a cosmic time lapse. Now imagine that this might actually happen to you if you fell into a black hole, not metaphorically, not in science fiction. According to the physics we understand today, time near a black hole behaves in ways that are so strange that it almost feels like reality itself is breaking. Black holes are already among the most mysterious objects in the universe. They form when extremely massive stars collapse under their own gravity, compressing matter into an incredibly small region of space. The gravitational pull becomes so intense that nothing can escape once it crosses a certain boundary called the event horizon. Not light, not matter, not information. That is why they appear completely black against the background of space. But the real mystery is not just that black holes trap everything that falls inside. The real mystery is what they do to time. To understand this, we need to start with an idea from Einstein's theory of relativity. In everyday life, we think of time as something that flows the same everywhere. A second is a second whether you are on Earth, on Mars, or in another galaxy. But relativity tells us that time is not absolute. It is flexible. It can stretch and slow down depending on gravity and motion. Gravity does not just pull on objects. It also bends space and time together into what physicists call spacetime. When a massive object like a planet or a star sits in spacetime, it curves the fabric around it. This curvature is what we feel as gravity. And when spacetime bends strongly enough, time itself begins to slow down. This effect is called gravitational time dilation. The stronger the gravity, the slower time moves relative to someone far away from that gravity. Here on Earth, the effect is tiny, but it is measurable. Clocks on satellites tick slightly faster than clocks on the surface of Earth because they experience weaker gravity. GPS systems actually have to correct for this difference. If they did not, your phone's location would drift by kilometers every day. But near a black hole, the effect becomes extreme. Imagine a spaceship approaching a black hole while another observer watches from far away. As the ship gets closer to the event horizon, the gravity becomes stronger and stronger. To the astronauts on the ship, everything feels normal. Their clocks tick normally. Their heartbeats feel the same. They can talk, think, and move as usual. But to the distant observer, something very strange happens. The clocks on the spaceship appear to slow down. Every second that passes for the astronauts looks longer and longer from the outside perspective. Their movements become slower. Their voices would sound deeper and stretched out if you could hear them. As the spaceship gets closer to the event horizon, the slowdown becomes more dramatic. Seconds become minutes. Minutes become hours. From far away, the astronauts appear to move in slow motion, and at the exact boundary of the event horizon, something astonishing occurs. To the outside observer, time for the falling astronauts appears to stop completely. They would seem frozen at the edge of the black hole forever. Light coming from them becomes increasingly redshifted and faint until it eventually disappears. From the outside perspective, they never actually cross the event horizon. They simply fade away as if time itself has trapped them. But here is the twist. For the astronauts themselves, none of this happens. From their perspective, they cross the event horizon normally. Their clocks tick normally. They do not feel time slowing down. They simply continue falling. This difference in perspective is one of the most fascinating aspects of relativity. Two observers can experience completely different versions of time depending on where they are in spacetime. So what happens after you cross the event horizon? This is where things become even more mysterious. Once inside a black hole, the structure of spacetime changes in a dramatic way. Outside the event horizon, you can move in different directions through space and choose your path forward in time. But inside the event horizon, the geometry of spacetime becomes so warped that moving toward the center becomes as unavoidable as moving toward the future. In other words, the singularity at the center of the black hole is not just a place in space, it is effectively a moment in your future. No matter what you do, you cannot avoid it. Just as you cannot stop tomorrow from arriving, Anything inside the event horizon cannot avoid eventually reaching the singularity. The singularity itself is one of the biggest mysteries in physics. According to Einstein's equations, it is a point where density becomes infinite and space-time curvature becomes infinite. Our current understanding of physics breaks down completely there. But what happens to time as you approach it? The answer depends on the size of the black hole. If the black hole is relatively small, such as one formed from a collapsing star, tidal forces become incredibly strong as you fall inward. Gravity pulls much harder on your feet than on your head, stretching your body like spaghetti. Physicists actually call this process spaghettification. Time would still feel normal to you, but the forces acting on your body would increase rapidly. However, if the black hole is supermassive like the ones found at the centers of galaxies, the situation is surprisingly different. These black holes can contain millions or even billions of times the mass of the Sun. Because they are so large, the tidal forces at the event horizon can actually be relatively gentle. In theory, you could cross the event horizon of a supermassive black hole without immediately noticing anything unusual. But the strange behavior of time would still be there. While you fall deeper inside, the outside universe continues evolving. From your perspective, your journey might take only minutes or hours before reaching the singularity. But because of the extreme time dilation, the entire future of the universe could pass outside during that time. Stars could burn out. Galaxies could collide. The universe itself could age billions or even trillions of years. Some theoretical models suggest that if you could somehow look outward while falling in, you might see the future of the cosmos speeding up like a fast-forwarded movie. Eventually, the universe might grow dark as stars die out and galaxies fade, all while only a short time passes for you. But reality might be even stranger. Quantum physics adds another layer of mystery to black holes. In the 1970s, physicist Stephen Hawking discovered that black holes are not completely black. They slowly emit radiation due to quantum effects near the event horizon. This radiation is now known as Hawking radiation. Over incredibly long periods of time, black holes can slowly lose mass and eventually evaporate. For stellar mass black holes, this process would take far longer than the current age of the universe. For supermassive black holes, the timescale is even more enormous. But this raises a fascinating question. If you fall into a black hole while it is slowly evaporating, what happens to you when the black hole disappears? Physicists still debate this problem today because it connects to something known as the black hole information paradox. According to quantum mechanics, information about physical systems cannot simply vanish. But if black holes evaporate completely, what happens to the information about everything that fell inside? Some theories suggest that information is somehow encoded in the Hawking radiation. Others propose that black holes may leave behind remnants. There are even ideas involving holographic principles, where information is stored on the event horizon itself. All of these possibilities hint that our understanding of space, time, and gravity may still be incomplete. There are also speculative ideas about what might exist inside black holes. Some theories suggest that black holes could connect to other regions of spacetime through structures known as wormholes. Others propose that the interior of a black hole could lead to a new expanding universe. These ideas are highly theoretical and currently unproven, but they show just how much mystery surrounds these objects. What we do know is that black holes push the laws of physics to their limits. They combine the largest scales of gravity with the smallest scales of quantum mechanics. They twist spacetime so severely that time itself can slow, stretch, and almost come to a halt, depending on who is observing it. And perhaps the most fascinating part is that these objects are not just theoretical anymore. Astronomers have detected black holes throughout the universe. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow at the center of the galaxy, M87. A few years later, another image revealed the black hole at the center of our own Milky Way galaxy. These observations confirmed that black holes are not just predictions of equations, they are real cosmic objects shaping the structure of galaxies and the evolution of the universe. Yet, despite decades of research, the question of what truly happens to time inside a black hole remains one of the deepest puzzles in modern physics. Does time end at the singularity? Does it continue in ways we do not yet understand? Or does the answer require a completely new theory that unites relativity and quantum mechanics into something deeper? Scientists around the world are working to answer these questions, studying gravitational waves, observing black hole mergers, and developing new theories of quantum gravity. Each discovery brings us a little closer to understanding how time behaves in the most extreme environments in the universe. But for now, black holes remain cosmic laboratories where the rules of reality bend in ways that challenge our intuition. They remind us that the universe is far stranger than our everyday experience suggests, and that somewhere out there, time itself may flow in ways we are only beginning to imagine. If you enjoyed this video, make sure to like it, subscribe to the channel, and turn on the notification bell so you don't miss the next one. And before you go, tell me in the comments what topic you want to see next. Your ideas often shape future videos, and I would love to hear what mysteries of the universe you are curious about next.